And now we will do the elastic collision. This is the one where we have M1 moving at V1 initial and M2 moving at V2 initial. And the only requirement is that they will collide, right? So in this case, clearly M1 needs to be moving a little bit faster than M2 or it'll never catch up. The way we're going to solve it, they could be going against each other. All kinds of things are possible. Positive numbers are to the right, negative numbers are to the left. We know we have to conserve momentum P. So that would mean M1 V1 initial plus M2 V2 initial. Your initial momentum must be equal to your final momentum. M1 V1 final plus M2 V2 final. Like that. So there's one equation and two unknowns we have to solve for. Nothing is sticking together here, so we don't know that those are the same or anything. And then we want to conserve the kinetic energy. Well, we say 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 final squared. Bueller plus 1/2 M2 V2 final squared. There we go. Now, we have two equations and still just two unknowns, V1 final and V2 final. So in principle, we're done. But if you go doing algebra and trying to solve for V1F or V2F, you'll almost certainly end up in some algebraic nightmare, torture. So what we actually do is we look for algebraic opportunities to simplify this. And rather than doing it every time you do a problem, we like to find them all once. And then once we find some simple algebraic opportunity here, we'll use that as the second equation rather than this, because this has these squares in it. And that only can possibly lead to problems, okay? So let's look for algebraic opportunities. And if you look at this and say, I would never have thought of those, that's fine, because I'm just showing you how we get a formula that you're going to use. Okay, so I looked at this, algebraic opportunities, there's an obvious one. Multiply this by 2, right? Get rid of all the halves. Done. All the halves are gone. What else could you do? You could group it by m's, right? Here's m1s times something, and here's m2s times something. All the v's are different. So let's do that. Let's get rid of the halves and group it by m's. So you're going to get m1 times v1 initial squared. This m1 is going to come over here minus v1 final squared. That'll be the new left side. And the right side will be m2 v2 final squared minus, and they're going to bring this one over, v2 initial squared. All right. So we took our energy equation, we wrote it like that. It's still full of squares. Too bad. But notice, it's the difference of two squares. Ooh, doesn't that sound familiar from junior high? The difference of two squares. A squared minus b squared, yes, is equal to a plus b times a minus b. So we use these difference of two squares. I don't know if that's how you used to write it or not. Let's see. M1 times V1, 1 initial plus V1 final times V1 initial minus V1 final. Sorry. Oh, whoops. Slipped out of my hand. I'm not upset. And then this equals M2 times V2 final plus V2 initial times V2 final minus V2 initial. All right, we just applied our difference of two squares. All right, so now we have that. This is still just the energy equation. But now let's look over here at this equation, because now we have all these sums and differences. So now let's get the P, the momentum equation, also in terms of those sums and differences. All right? So we have combined V1 and VF, or V1I and V1F. So here's V1I and V1F, and they both have an M1 in front of them. That's convenient. So let's write M1, and it's V1I minus V1F. All right, that is this side. And on the other side is M2 times V2F minus V2I. All right, so still two equations, two unknowns. There's K and there's P. Okay. Now, here's the weird part that you probably wouldn't have thought to do, is we're going to divide the two equations. Now, you can divide equations. If this equals this and this equals this, then the ratio of these equals the ratio of those. Why not? Okay, so we're going to divide the equations. I guess we're putting K over P, if you really must know. Okay. So if we divide K over P, what do we get? Hey, the masses cancel. M1 cancel. The difference terms cancel. So we get V1I plus V1F is the only thing on the left. That's weird. And what's on the right? M2's cancel, differences cancel. Look at that. V2F plus V2I. That's always going to be true. Why? Is that saying something about center of mass or relativity or what? No, it's not saying anything. It's just sort of a mixture of the kinetic energy requirement and the momentum requirement. And we've just done some algebra to get rid of the squares. That's really all it is. So now you have two equations, two unknowns. You can still use this one, okay? You might say, hey, we put it in here, but this is still the energy equation. We just use the momentum part just to simplify it a little bit. Still think of that as a kinetic energy requirement, and you can think of this as the momentum requirement. And now we have two equations, and there's an unknown, and there's an unknown, and there's an unknown, and oops, there's an unknown, and there's an unknown. So next we'll show you how to finally bring this all the way down to useful expressions. So we just worked out for an elastic collision with two different masses approaching each other at different velocities, and we have an elastic collision where we conserve energy. We came up with these two equations. This is just conservation of momentum, where here's your unknowns, V1 final, V2 final. And then this is really sort of an algebraically altered version of conservation of energy, or again, V1 final, V2 final. So if you were to be given a problem about an elastic collision where you gave some initial conditions and you just had to solve for some final velocity, you could probably just use these. You could start plugging in your numbers and just solve for V1F or V2F. But we actually do like to go through and give sort of a general symbolic answer. We like to solve these for V1F because the solution gives you a little bit of intuition for what's going to happen. Rather than just solving a specific problem, you can maybe learn things about how systems will behave. So all you got to do is be able to solve two equations, two unknowns, solve this for V1F, solve this for V2F. If you do, you might end up in a little bit of an algebraic nightmare going through loops and pages of algebra. So I'm going to show you the right way to get there. And also because I had the world's greatest algebra teacher, Mr. Owie. Yes, there you see Mr. Owie. Yes, he hated consonants. So anyway, what? Oh, come on. Get that out of there. Come on. Okay, do we have a time for like a therapy break? Okay, no, let's just keep going. Let's just pretend we didn't see that. Okay, so what we're going to do is figure out the smart way to do this. The smart way is we want to solve for V1F is to get this by itself, but don't divide through by the M1. Let's keep the M1 here. M1 V1F equals, and then we'll say, oh, it equals M1 V1I, the initial velocity, plus M2 V2I, the other mass's initial velocity, minus M2, and now we've got V2F, which is an unknown we don't want. So then we'll solve this one and stick this V2F in there. This is the quickest way to get there. So this is equal to V1I, that's an initial known, plus V1F, that's the one we're looking for, that's good, and then minus V2I, another initial one that we know. So there's our unknown, and there's our unknown right there. Not if, there we go, 1F. All right, and then what you want to do is we're solving for V1F, so you get them all on one side. All right, so we have minus M2 V1F. So if we bring that over here, that'll become plus M2 V1F. So So we have m1 v1f plus m2 v1f. We can go ahead and pull out the m1 plus m2 v1f. All right, and let's just see what we have left over. We have, what do we want to do with what's left over? Let's go ahead and start separating things. We have m1 v1i, and we have minus m2 v1i. So let's go ahead and pull our m1 minus m2 out of that. Right. m1 minus m2 v1i. Okay, and then what else do we have? We have the v2i's here. So we have m2 v2i minus m2 minus v2i. So those two minuses become a plus, and you get a 2. Interesting, plus 2 m2 v2i. All right, so now we're going to solve for the thing we're looking for, v1f. We're just going to bring the m1 plus m2 under the bottom. All right, so we get v1f. This is the real deal. Mass 1's final velocity in this case is m1 minus m2 over m1 plus m2, and all that times v1 initial. Plus, so it's got two big terms, plus, and then we've got 2m2 over, again, the sum, m1 plus m2, and all that times v2 initial speed. And this is sort of the general solution for how fast mass 1 will go in this collision, no matter what the values of v1 and v2i and v2i are, or how fast they're initially going. They have to be going in a way where they will actually collide, right? They have to actually be heading towards each other. But that's how you get it. We could do the exact same algebra to get v2f. Almost identical steps, and we would find we get an almost identical solution. We would get the 2m1 over m1 plus m2 on this side, and that would be times v1i. v1i plus, and then we would get the difference over the sum, m2 minus 1 minus m1 over m1 plus m2, and this would be the v2i part, v2 initial. That's the other one we could get with essentially the same algebra. So we were able to do that in just a few steps because I knew the answer, right? I was cheating, right? So I know that this is the answer. I know you're going to have an m1 plus m2 in the bottom. So that's how I knew we're trying to work an m1 plus m2 over here. Right? So there's tricks to making things work out on the board. Let's see. So this is the general solution, and I told you that you can get some insight from this general solution. And you're looking at it and thinking, you can? But you can in special cases. All right. So let's think about a couple of special cases. One is, what if the masses are equal? So let's over here look at equal masses. m1 equals m2, right? If m1 equals m2, let's look at this whole big mess. If m1 equals m2, this term is 0, right? m minus m is 0. So v1 final doesn't even depend on v1 initial. Weird. What if m1 equals m2 here? This is 2m, and this is 2m. And it cancels, and it's 1. So what you get is that v1 final, how fast this one is going in the end, is the same as v2 initial. That's weird. All this complicated formula reduces just to that. However fast this one was going at the beginning is how fast this one goes at the end. Let's look at this one. Same thing's going to happen. If m1 equals m2, then this becomes 1. So you get v2f equals v1i plus, and what does this make? 0 plus nothing. So what this tells us is if the masses are equal, they exchange velocities. Is all that happens. And you can imagine this would do a good job of conserving momentum. Right? It's two masses, the same mass, they have one set of velocities and they just switch, and then they change the velocities, therefore the momentum would be conserved. We can look at a couple of cases of this. Here are a couple of these carts. One has a spring-loaded end on it, so it can have kind of an elastic collision. and I've added a weight to this one to make up for the extra mechanics in this one. Right? So the weights, the masses are pretty much the same. So if I leave this one here not moving and say this one we're going to give some velocity, they're going to crash into each other, and they should just exchange their velocities. So let's see. And they did. You saw this one got the velocity that one had, it stopped. This one took off at about the same speed, or velocity. You can kind of see it with them moving as well. I'm going to move this one kind of slow, and I'm going to move this one at it kind of fast. And you can probably kind of tell that obviously this one goes fast and this one goes slow, but pretty much at the same rates that they were. So again, two objects of the same mass in an elastic collision will simply exchange velocities in this 1D world we're living in right now. Let's look at another insight that we get from these equations. What if M2 is stationary, is not moving? We did sort of one case of that here, but let's look at it more carefully. Now the masses are not necessarily equal, but M2 is not moving. That means V2I is 0. So that's just going to simplify these. It's going to take away this term. Right, so then you're going to say velocity 1F is the difference equals M1 minus M2 over M1 plus M2, right, times V1I, or V1I. Right. So what this tells you is if M1 is less than M2, M1 bounces back. It'll bounce off of something if it hits something bigger than it is. Right, so we can show you that. We can take M1, M2. Here they're the same mass. Right? So that would be a case where it would not move at all. V1 final would be 0. We did that over there. But now let's make M2 heavier than M1. Right? So now it's got a lot of extra weight on it. Now if I send in mass 1, that should be a negative number, right? V1F is going to be negative. It should bounce backwards. And there it goes, bounces backwards. This one goes forward. If we look at the case where, let's see, if M1 is greater than M2, then it's going to barrel through is the phrase I'll use. Right. So we can show you that as well. We can put the larger mass on M1. In this case, M1 should push M2 along and just keep on going. Let's see. Yep, there you go. Kept going. And then I guess the final insight we can get from this is to say V2F is the 2M1 over M1 plus M2. And V1I. Right? And all you get from this is no matter what the case of one greater than the other, this is always positive. M2 will always go forward. Right? You can't really imagine, the only way it could go backwards is if this one also went backwards, and then that would clearly not conserve momentum if everything started moving that way. So we know that all these equations make sense in these limiting cases. And that's what the general solution is good for, to learn some sort of intuition for how things interact.